here. Now, what I want to do is this, guys. If you really had trouble with this, make sure you're doing this with me. Make sure your calculator's out. This is a problem. These kinds of problems, it's like there's no reason you should get these wrong in the AP exam. It's just like, can you use a calculator? That's all it's asking. Okay? It really is. A lot of these types of problems are just, can you actually type them in? So, let's begin this. I'm going to open my calculator actually at the same time so that I can show you what I would have done on mine. Because there's certain tricks along the way that some of you might have picked up on. Thank you, Edgar. All right. Anybody get 11 right? I got a few, right? Okay. Anybody know what to do to start?
I didn't. I get out.
Or you can just read the problem.
Okay, find the average value of the function over the given interval and all values of x.
Oh, interval is spelled wrong. Nobody picked up on that. There's nobody.
Your math
Still shouldn't do that. Okay, so what's the formula, Christian, right away for average value?
1 over b minus a.
Times. Very good. From where to where?
From 3 to 7.
So thus that is eta. Thank you. Okay, that's our formula again, average value. Now, the easy part of this problem is to simply find the average value. That's the easy part. Okay, that's the first part here. Second part is the harder part. And once I show you graphically, you're going to be like, oh, that's so easy now. So let's do this. I got 1 over 7 minus 3 integral x squared plus 4 over x squared from 3 to 7. Now, here's what you could have done for this problem. You could have divided this in, got 1. You could have divided this in, got 4x to the negative 2. You could have integrated, done all the work. Please don't do it if it's a calculator problem. Take your time and go to your calculator and make it easier. So if I go to my calculator now, I want to have that function, x squared plus 4 over x squared. So I go to y equals, parentheses, please, x squared plus 4 all over, parentheses. I don't even need them, but I'm putting them there just for the heck of it. Good. Whoa, 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 whoa.
Thank you.
It would be cubed there, yeah. So, for this part now, let's go ahead and integrate. What's my command to integrate, people?
Go to calc 7.
Good. Calc means calculate. I think of it as calculus, to be honest, though. Because look at the functions. The 0 of the function, that's like saying, okay, the roots. The value is the y-coordinate. Min, max, intersect, derivative. Okay, I think of calculus when I see it, just to remember. What number I press?
7.
Okay, look at the integral sign. It's there. Press 7. Now, where do I want to integrate from? From where to where?
3 to 7.
So lower limit is?
3.
Enter. Upper limit is?
7.
Enter. And boom, there's your area. Now, 4.76, that's my area. But that's the integral, isn't that the integral? I have to multiply that by 1 over what?
4.
It was, remember, 1 over 7 times the, 1 over 7 minus 3 times the integral 3 to 7.
So it's 1 over 4 times.
So this is the integral. Again, the answer we got is simply the integral's value, 4.76. So we got to multiply that by 1/4. So let's go into our calculator, multiply by 1/4. 4.761. Now, another way to do this, by the way, without even going to the graph, if you want to see it for the other people, math, over to numerical, go to integration. Oops. Go to integration, hit enter. What function am I integrating? y1, y2, y3, y1. Vars, over to y vars, enter, enter. There's y1. I want to integrate from where to where?
3 to 7.
3 to 7. I think it's just 3 comma 7. We might need an x in there. If this doesn't work, it means we need an x. Let's see. Yeah, let's see. Hit go to. It'll show me where to go to. So I need to probably put an x in the end to show them integrating with respect to x. Oops. What did I do wrong? Let's try x37. X. Edgar, can you check the actual command if this is wrong? See what the input should be? Look it up. Yeah, see, something's wrong. What is that we're working for?
What do I actually check for?
Just Google integration.
Why don't you try the less than or equal to thing? X less than or equal to thing. Try that too.
We could try it. I don't think so, to be honest, though, but I could try it. What do you want me to do? Input the domain of it? I mean, we could try it. 3. Let me go to second test. Less than or equal to. I don't think this is going to work, guys. I would love to see it work, but I really don't think it's going to. I don't think these are made for this. They're for like logic testing when you write codes. Yeah. To be honest, I really didn't expect it to. Sorry. It's giving me an error in the parentheses though, which makes me think that I have a need of another comma somewhere.
Maybe.
When I did it earlier. Okay, so let's make believe. You know, it's not make believe. I forgot how to do this. Okay, I did this so long ago. I always use the graph anyway.
Wait, what did I do?
So let's say I wanted to figure it out.
Moneyball.
Okay, let's say I wanted to figure it out. TI-83 integration. Oops. Integration. Home screen. Because it's probably going to give me the way to do it without the home screen. So let's click on this. Okay, I want the integral of this. I go to math. I type this in. Let's see. First argument is the integrand. Okay. Let's see. Second argument is the variable integration. Okay, so it's y1, then it's x. Good. Third argument is lower. Fourth argument is upper. That's exactly what I did.
No, you put the x into n. Yeah, you did.
But then I switched it. I put the x here, then I switched it to that.
Really?
Yeah.
Oh, but you know what? It's using function integrate. That's why. It was the wrong command. I had a feeling. Okay, let's go back. Go down a little bit further.
Wait, why
It doesn't know why you.
It's two different things. Watch. Let's go over.
Oh, it's at the bottom.
It's under math, and it's under function integral, not under numerical. This is probably doing the integer, or the lowest integer function, which is called the step function. It's a different thing to do, which is fine, but let's go back. So it's under, sorry, let's do it again. We're going to go to math, and then just press up after you press math, and go to FN integrate. It's number 9.
Does this method take much longer? Or math 9.
If you do, yeah, exactly, just math 9 works too, that's why number 9. Personally, I don't think so. I mean, it doesn't matter to you. But Kenny, what you can do is this. Watch this. Insert. So now it's taking a quarter of it. I'm getting the actual answer of the average value. Remember, do we have to divide it by 4? So if I put a quarter times the integral, isn't that what the average value is? So I can do it maybe a little bit quicker. Yes, you get it to the decimal. And you know what else you can do is you can then hit math, enter, enter, and convert to fraction. And we'll do that. So comma x, comma 3, comma 7. All right? Now, watch what this gives me. Now this number, if I press watch, math, enter, enter, there's the fractional value you saw. Okay, that's why it's a little bit important. If you did it on the graph, it's fine, but then you got to go from the graph and figure out which choice matches up numerically. This is a lot easier. So let's go back to the test. If I can get there. All right. So 25 over 21 is my answer. So that's out, and that's out. Okay, right away it's only 2 choices. But the next part is the tougher part. Does it intersect the graph once or twice? That's pretty much what this is asking. Okay? Does it intersect once or twice? Why 1 and why not 2?
Not negative?
Because it's exponential? Because it's like rational? Because it's rational?
Well, guys, you're all missing the one part I noticed. You're thinking logically, but look at the graph. It's clear they're going to intersect twice. It's a flat line at 25 over 27, which is 1.17 or 1.19. Okay, so if I were to graph this, watch what I do. I go to here, and I'm going to graph, what was it, 25 over?
21.
Thank you. Okay, that's the value of the average value. I hit graph now, and I'm going to see there's an intersection there, and there's an intersection there. Why is the answer only one of them now?
Because of the domain? No.
Come on, think. What was it?
The domain?
The domain, very good. It says on the given interval, doesn't it? What's the given interval, guys?
3 to 7.
3 to 7. So this is going to intersect before the 3 there. My actual number is root, what is it? Root 21. So root 21, let's figure out where that actually comes into play. The function's value, okay, it says again, find the average value of the function over the given interval and all values x in the interval for which the function equals its average value. So what I want to find really is my intersection here. How do I find the intersection?
Isn't there something in calculus?
Yeah, go back to second, calc, go to intersect, number 5, hit enter. On the first curve it says, where are you? Well, I'm going to press to the right. See that little dot? It's coming down there. I'm going to press enter. Now the dot is flashing on the intersection. I'm going to hit enter. Then it's the second curve. It's right in the same area. Hit enter. Hit enter one more time. Well, I get this number, 4.582. Take a look at your answer there. Square root of 21 is 4.582. Okay, look at your actual choices there. Now, what if I wanted the exact value? I have to do it by hand to get that actual radical of 21 there, okay? I have to set the functions equal and solve by hand. But here, this is the square root of 21. Now, it does intersect that negative radical of 21. So a lot of people end up choosing the one that has both answers. But as Edgar said, our interval of inspection was really from 3 all the way to 7. And our intersection is actually right here. That's where it actually intersects. The area is all there, so I apologize. See all that area under there? Ignore that, it's all shaded in. But again, where would it be over here? 1, 2, 3, 4. There's the actual intersection on that side. So there's 2 intersections, but our domain of interest is from 3 to 7. Okay, 3 to 7. Now, I've got a question for you. What about this? What if it said, what is the value of the function when it intersects? What's your answer? 1.1?
Yeah, 1.9.
1.19. What was 1.19? What did we say a minute ago? What was that really?
25/21.
So the value is what you get, right? The average value of the function is the y value always. Again, think about it logically. This is a horizontal line. The horizontal line is represented by the graph, and it's not up here, sorry. The graph of 25 over 21. Well, 25 over 21 is about 1.19. So a vertical line crossing here has a value of 1.19, thus that's why the y value has to be the same. Okay, because this is a location, it's an intersection. The x value is the important part that we're looking for. Okay, the x value. All right, let's go to the second one. Evaluate the following integral from 0 to 4 radical pi. Again, guys, for this kind of a problem, just do it by calculator. You don't have to actually do it by hand. This would be a mess to do by hand. What would you use to do this by hand? Now, what would you be in this case? Even though u's already there, I know. What would your real dummy there? Yeah, you know there's u already there? Just make the u's x's in your head. So what's the u value? What would you pick for u here? 2u squared. Again, if we call this x, I know it's u, but they do that on purpose because u is just a dummy variable. Call it back to x. Now, if you let u equal 2x squared, you get du dx equals 4x. And when you plug that in, it'll cancel with that x right there. And you'll really be integrating cosine of u, okay? Which turns out to be sine of u, yes, but that's what you're integrating. And it's probably over 4, I think, right? Should be over 4 dx. Anyway, if it's in a calculator section like this one was on the test, please go ahead and just integrate it on your own. So, anybody have a question on this after we did what we just did? What's the only difference that makes this a little tougher?
The u's?
Yeah, I mean, no, the pi, that's it. Call the u x, sure. So type that into your y1, x cosine of 2x squared. But this 4 radical pi and this 0 here, the 0, that's fine, that's easy. But the upper limit, people get confused with 4 radical pi. Just literally type in 4 second square root second pi, close parentheses, enter. Okay, enter just like you would enter pi. Everybody know where pi is on the calculator? Okay. Next one. Absolute value. Why is this one tough?
Negative.
Because it's a positive negative portion first, good. So you're integrating what? X minus 3 is a graph that starts over at 3, and it looks like this. Remember, this is my h, and my k is out here. So h is negative 3, so I shift 3 units to the right. So that's the graph. And I'm going from 1 to 4. So my integral is from 1 to 4. This is 2 right here, that's 3. So I'm getting this area, and then I'm getting this area right here. So if I did this by hand, I would have to use a piecewise function. This is one line from 1 to 3, and then it's a whole other line from 3 to 4. If you're using your calculator, how do you do it?
So you do a math and type it in, and after
Okay.
divide it.
So we go to y. Let's clear these out.
Isn't it a math? Yeah, isn't it a math? After divide.
Number.
Did you do the integral first?
Yeah.
Do the integral
We can
and
do
then
it.
put absolute value inside of it.
We could do it that way. I'm just showing you on the graph. Same thing. Absolute value of what? X minus 3. Okay, on your graph, you're going to see it looks exactly like we just said, and then you want to integrate. Okay, second integrate, 7, 1, 4, and that's exactly what we just showed. 2.5 approximately. Okay, 2.5. Where do you see 2.5, guys? Again, why is it an approximation there? Why is it a little bit off? Why is the calculator not giving me the exact answer?
Because the calculator is easy.
Calculator uses a technique called the numerical integration. Okay, and what you're going to learn, if you go on to study other levels of calculus, that things that can't be integrated are numerically integrated. And they use what's called the trapezoidal rule. So instead of using all the pieces like the Riemann-Sums pieces, you're using the trapezoidal rule. Man, the innocent one. What was that, huh?
You know that, right? I'm not. Okay, you did bad.
I got guilty.
You have to look at her face like it wasn't me. Yeah. So again, for this problem, what they're doing is they're actually fitting a bunch of trapezoids in here. Okay, a bunch of different trapezoids at different shapes and different angles. So it's an approximation technique. That's why it's a little bit off there. Okay, but the actual answer is, the numerical answer is without all of this stuff right here. Okay? Alright, that's those three. Let's go on to part twos. The fun stuff.
My hair.
Used to do it, be
You
first.
can't even believe that now.
Two, you're just related to each other. Be your house. What?
There's some stuff now.
With part D first?
Yes.
What's the difference? Hey, I'm not going to do it. I'm just going to ask for answers, okay? Guys, what's the domain here? What's the domain?
4 to -4 to
-4 where?
infinity.
Infinity and...
Beyond.
I can't believe I forgot the rest of the managers.
I know.
I know, Kenny, you just left it blank. I was so surprised.
I
So the other way you can write this is x greater than or equal, sorry, bracket, sorry. Thank you, Karen.
Wait, switching it Thursday positive?
Now,
What's Adam? 7?
besides looking at the graph, because some of you did that, and that's fine, how do you actually figure this out? How do you figure out the domain analytically, by hand? Like, you can look at the graph, and what you're going to see is the graph looks like this, right?
Don't you go like switch?
Okay, I could do a beep test, sure, on the graph, though. But I'm saying, Jasmine, from this equation, how can I figure it out without the graph? Okay, let's think for a second, right? Domain is our x restrictions. If x were -10, what would we get underneath? Negative 10 plus 4. Can you have a square of -6? What is it?
Imaginary.
Imaginary. And imaginary parts cannot be graphed here. So what you need to do is say that the integrand, integrals, the radicand, the radicand must be positive, right? Again, the radicand cannot be negative. It's got to be greater than or equal to 0. It could be positive or it could be 0. Just move it over. Subtract 4, there's your answer. That's all you got to do to find the domain. Same thing with natural log. Write that down, please. Same thing with natural log. Natural logs cannot be negative. Okay? Natural logs, and they also can't be what?
Imaginary?
0. Natural logs can't be 0 either. Okay, there's a horizontal asymptote. Remember the log function? The log function looks like, if I'm correct, the log function looks like this, and there's a horizontal asymptote here. There's a horizontal asymptote there. Actually, wait. No, the log function doesn't look like that. Let me erase that. That's exponential growth. Sorry. Yeah, we did. I hope so. Tell me I'm not. Oh, no. Oh, yeah, good. All right. ln of x, close, delete. Graph. That's why. Okay, it's the inverse. All right, so the exponential growth function looks like this. Okay, where it has an asymptote along the x-axis, an x-asymptote, whereas this one has a vertical asymptote. This is the log function right here. And what you're going to notice is that the log function becomes asymptotic. So it will never get to the y-axis. Therefore, the domain of a log function is x is greater than 0. Okay, again, the natural log function is x is greater than 0. But what if I had the natural log of x minus 5? How do I figure out its domain? I'm telling you that the natural log has to be bigger than this. Why? What's less than 5? What's going to cause there? Good. It's going to be cause. If you put a 4 in here, what's 4 minus 5? -1. And we said you can't have it. What if you plug a 5 in?
They can't find either.
Because it's 0, right? So it's just everything greater than 5. How do I get that? I start by setting this greater than 0. The argument must always be greater than 0. That's my rule up top. and then I set whatever the argument is greater than 0, move the 5 over, and that's your domain for natural log. Are we clear on that? What's the range for a natural log function? And? Sorry. Yes, and to negative infinity. The range, look at the graph, guys. This is going to go down forever. This technically rises forever. The range is just y, e, r. The range is all real numbers, or we can say, okay, either way. You have interval notation, set builder notation, one or the other. All right, sorry, that's going to come up in problem 3 on the last one. That's why I did that, which we had a lot of trouble with. We'll get to that. All right, first one, so we said is that. Integration-wise, somebody give me part. So part 1 is this, yes, x is greater than or equal to negative 4. What about part 2? Can I get a number for part 2? A lot of you had this right.
10.46.
What is it?
10.46.
Okay, Rakab, thank you. 10.46. Another one for the second one?
11.97.
11.97. Now, without telling me the last answer, tell me what it should be like.
It could be.
Combination of both. Very good. Again, if you're going from negative 2 to 3, then you're going from 3 to 7. It's like you're going from negative 2 all the way to 7. So just sum these numbers together. You're going to get 3 here, carry the 1, 4 there, carry the 1, 2, 2. Okay? Again, just add them together. You don't have to actually do it. It's more work, guys. Don't do that. Now, why did I do that? I made this problem up. Why did I do that as the preface to this?
To make it think
Show us
more.
that, you have to do that.
Measure
Next
you.
one,
That's how this works too. Take a look. Watch. Switch these two around. Switch their locations. I'm going to drop the dx's real quick. If I go from h to u, then I go from u to p. It's like I'm going right from h to p. Again, just like I did here. Negative 2 to 3, 3 to 7 was just negative 2 to 7. So h to u, and then u to p. This actually results... I gotta get this off my screen. This is really annoying me. Come on. Why is that doing that? It's still on there, though. All right, anyway, this goes from really h to p. That's what that resolves to. But we still have this other right-hand side here. Okay, see this other right-hand side? And take a look at it. You want to say, like, j to p, then j to k. By the way, JK, I think I saw that. I thought I was doing my math. So j to p and then j to k. But I can't go from j to p then j to k. I got to have these two being the same, don't I?
Yes.
Just like here, I had to switch these so that the u matched up. That's the only way this works. So what can I do, Carrie?
Switch it around.
Switch these two around, right? So if I switch these limits, Carrie, and I go from p to j of f, and then I go from j to k of f. Now, Carrie, what should happen to that negative sign?
That's positive.
Whenever you switch the limits, you're negating the integral. That's one of our rules we talked about. So this is really like minus a minus. So this becomes plus. Now, look at this again. P to j, j to k. These kind of cancel each other, right? And you're left with just p to k. And now you have to add these. H to p and p to k is really cancel the p's, is just h to k. Okay, that's your final answer with the dx and all that stuff. Okay, h to k. Again, that was a tough one, I know that. It's not an easy one right away. All right, let's look at the next problem. Oh, by the way, guys, did you notice? How long did that take me to really do?
3, 4, 5 minutes.
Okay, so this is why this problem, I made it up. It would not be a real AP problem because it was too short.
These games just get on the curve at home, right?
Well, to be honest, Kenny, the problems that they have for integration in part 2 are all applications like volume and the stuff we haven't done yet. So I had to make up some of the problems. The only one that's not integration was this one. And this was actually right off the AP exam. And people seem to have trouble on that one. Okay? Again, it's tougher when it's off the exam. They're a lot harder, the problems there. We're going to be doing a lot of them. All right, so for this problem, people really seem to mess this up, guys. I don't know what happened with your numbers, but a lot of people's numbers were way off. So you got to go back and look. I wasn't going to sit there and try all your numbers. Some people were off by like 0.5. Okay, I don't know why. Go back and look at your numbers. You must have made a mistake at one of the intervals. Okay, but if I were to do this, I'll do LRAM to start. You're going to say? I'm going to try LRAM just to take a look at it. What's my interval from 4 to 0? Over 4, which makes delta x simple. Okay, makes delta x 1. So for this problem, if delta x is 1, I know that each rectangle is going to be 1. What does this graph look like? What does the parabola look like?
A roller coaster.
Good, a U. So I start at the 3 because there's my y-intercept, and it's going to look like that. The graph really goes to the left, doesn't it?
But you're 0.
No?
But I'm going from 0 to 4.
He's going up.
That'd be the best route ever.
Okay? So start by doing this. And a lot of you drew that, that's fine. You really don't have to draw it once you get used to it enough, by the way. It's not required to draw it, just so you know. We did that to... I'm totally with you. But if for speed, if you know how to do it without drawing it, do it that way. So here I got left approximation, left, left, and left.
Yeah, I know.
And what is left going to do? Under, over, approximate. Under approximate. Because look, all of these missing areas here, here, and here that should be under the curve is all missing. So you're going to under approximate. What's the right going to do? Over. In the middle?
Average out.
Not average, but
Closer.
somewhere in between. You can't say average. Average is only when the function is what? Linear. When you have a linear function, MRAM is an exact average of L and RRAM. Okay, again, average those two. Only when it's linear. That was your quiz you had a while back. Okay, if you think of your quiz last week or so. Not a while back, really. All right, so doing this, I know that I'm going to have the area from the left side. What's my delta x that I'm going to factor out? It's just a 1. That's my width. You don't have to write it, but I would just write it for now. Okay, because of the fact that people forget this. Your width of all your rectangles is 1, so you factor that out. Now list all your heights. So I start with f of 0, plus, 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 plus. Good. But I get you there. Let's get one more in here. We're ran out of room. Okay? Again, why do I have 4 spots here, people?
Intervals forward.
Oh, no, because there are 4 how many?
Rectangle.
Rectangles. The interval could be 8. Don't assume that, okay? The interval could be from 0 to 8. So again, take a look. 1, 2, 3, 4. N equals 4. That's the number of rectangles. Now, how do you actually do this? I don't know what happened here. But just plug it in. I mean, this is simple math, guys. I plug in a 3 here. I plug in a 0, I just get 3. I plug in a 1, I get 4. I plug in a 2, I get 7. I plug in a 3, I get 12. Do it in your head. 0 squared plus 3, 1 squared plus 3, 2 squared plus 3, and so forth. You end up getting 10, 22, 6, 2, 6, 1, 2, 6.
That was stupid.
Okay? That's LRAM. RAM, what was RAM? 42?
Remember the first time?
What was MRAM? 33. Okay, 33. What was the exact integral for this?
33.3.
So what conclusion, Christian, can you make about this?
MRAM was the closest.
What is the closest? That's your conclusion, guys. Again, make a conclusion that is sound and valid based on your evidence. Again, the exact integral is this. Those are your other ones. What's the conclusion? MRM is the best.
So we have to rewind the point.
If you did, that's fine, and I'm not taking on points for that. Okay? But you messed up your number. That's where you lost points. Numbers?
I have no problem.
All right, last one.
Champion, my thing, I'm still.
All right. So this is not an easy problem. I'm telling you right away, guys.
That's fine.
Okay, and what I'm going to do is this. I'm going to put out what they give you points for, so you have an idea. Okay, and I'm going to the way here's how it looks. This is what the answer key looks like on the exam. They actually give the answer, and then they tell you what the points are allotted for. So I'm going to go over the answer, and then I'm going to put out the actual solution, so you can see all these points and how they break it down. This is the stuff that we're going to be analyzing for an entire month. Okay, we're going to be looking at the answer key and saying, where do the points actually come in? That is one of the most important things. And believe it or not, just separating this, just going like this, watch. dy e to the 2y, which many of you noted screwed up here. It's e to the 2y. 2y is the exponent. It's not e to the 2 times y. A lot of people wrote this. It's not. E to the 2y. Y is in the exponent, guys. Come on. It's clear as evident. There's be no confusion there. I mean, I can't really help you. So this right here, that's 1 point out of 9 right there. If you did that alone, you got 1 point. Okay? If you did not do this, and ready for this, and you did all the work for part A, you get 0 points. Again, if you screwed up this part and did an integral and got a different answer, you actually get 0 points. I'm not exaggerating. The separation, it says, note, 0 out of 6 if separation of variable is missing. That's what this is, you're separating the variables. Okay, so you gotta remember that's the key for these problems. Now, integrating both sides. This is where it gets tough. What's the integral over eta function? It's a repeat. But look at the, what's the what? A chain. So really, this is what? This is really e to the u. Okay, e to the u. Here's the trick, and I'm going to show you a trick you can memorize to avoid u substitution. Tell me, everybody, please, the derivative of e to the 2x. The derivative. Not the integral, but the derivative. What's the derivative? Times 2. Chain rule. Again, the derivative of this is e to the 2x times the derivative of the argument, which is just 2. The integral is e to the 2x divided by 2. It's the chain rule of integrals when they're basic. This only works when it's like 2x or x squared or something very basic there. Okay? So I wouldn't memorize that. Okay? I mean, I would memorize that. I wouldn't generalize that. I would not generalize. Okay? It doesn't work for all. It works for basic functions that are just monomials. Let's generalize and say monomials. That is correct. Okay, monomials. Binomials are different. So here, I've got e to the 2y divided by 2 equal to. Okay, so sorry, integrating. Integral of this, everybody?
X cubed.
Very good, Kenny. And notice, it's 3x cubed over 3. Okay? 3's cancel. What do I need at the end, guys?
Plus C.
Thank you. Plus C. You know what? You got a point for integrating this side. You get a point for integrating this. You get a point for the C. That's 4 points if you did that so far. Okay?
Yeah,
Again.
how many points I got?
And you probably got 4 points because you did that.
That was
So did I.
Okay? And they say 1 point for the antiderivative of y, 1 point for the antiderivative of x, 1 point for the constant of integration. Now, in order to find that constant of integration, what must I do next? Okay, solve for C.
Y. You say y and x.
y by itself.
Plug in what?
0 and 1/2.
Which is called our what?
Initial.
Initial, because it's 0. Particulars when it's not.
Still want to
Don't you think it is y equals f of x before you put your 0?
Theoretically, no. Check it out. Isn't C actually over here, Kenny? I wouldn't do that, actually. I would do it the other way. Then we can solve for y afterward. But you see what I'm saying? It's just easier this way. So for y is 1/2. It's e to the 2 times 1/2 all over 2 equals 0 cubed plus c. So c is just that. Well, what's 2 times 1/2, everybody? 1. So c is just e over 2. Dude, no, you don't need a calculator for that.
No, I don't know. I can't remember the value of e.
Oh, sorry, yeah. 2.71, approximately. Okay, so half of that, 1.355. All right, so here, for this value, this is what you're going to put in for c now. But we still have to go on to the next part and actually solve the differential equation. So as Kenny said, we got to solve for y still. Now, when you're solving for y, it might be important to actually use this form instead of the actual solve value for c. Doesn't matter. It's up to you guys to decide. So let's go ahead and solve this one now. So
Multiply.
it's going to run out of space. Sorry, guys. Come on. There we go.
However, we're writing this stuff on the computer.
You don't remember doing what?
Like, I don't know how you memorize where all your stuff are on the computer.
There are tabs on the bottom.
I know, it's just there's so many.
Scissor, cut. All right. So now I want to figure out what the actual solution is. What's my next step? Who remembers from the actual class? Okay. Why do you want to get rid of it? Why do you want ln? What does ln do? Okay. Before I do the ln though, what can I do with this 2 maybe? Move it up over here, right? Now it's going to be e to the 2y equals 2x cubed. Now I can write plus 2c, but it doesn't matter, remember?
E2 times.
C is a constant, though. Okay, c is a constant. So if I double it, it doesn't have any effect on it. Because we're going to solve for c in the end. Well, we already did solve for c. So don't worry about it right now. We'll do the whole thing leaving c alone, and then we'll plug in that value at the end.
E divided by 2. So you put in c, it'll be just be e.
Let's try it. Can we try it this way, and then we'll try it that way and check? I don't want to give you an answer, because I don't know. I wonder if that works. If I plug in, you're saying, plug in the e over 2 for c, multiply makes it just e, and then solve. I wonder. Let's do it this way, and based on our answer from this, let's try and make a conclusion before we try it that way. This is how I would solve, guys, this is how I would test stuff out, see if I'm right or not. I would actually solve it this way, then look at the answer and try and make sense of that. So let's solve it this way, get what we get, and then look and see if what Christian said would have worked. So what do I want to do to both sides now? ln. Why do I want to take the ln of both sides?
Get rid of e, so you got 2y.
Good, remember, ln of an e function, they drop off, you're left with just 2y. So take the ln of this. It's going to be ln of 2x cubed plus c. All right, cool. What's next? Divide by 2.
That was it.
Y equals 1/2 ln of 2x cubed plus c. What should I really put around this, guys?
Absolute value.
Thank you, very good. Okay, think about your absolute, oh no. I'm sorry, I said that wrong. When is an absolute value? When should there be an absolute value?
Oh, when...
Yeah, what is the integral of 1 over x? That's where it comes from. I figured that in my head. I just thought right away to jump to that. Okay? Yeah. Right away I was like, oh, in natural log, let's put the absolute value, but that's when we integrate that. Alright, so at this point you've solved for y, right? You've solved for y here. Now, I've got a question for you guys. You agree already?
Yeah, I agree.
If I have it set up like this, and I want to actually figure out my value for c here, what would I then do? Plug in, right? Let's verify that we get the same answer here, right? That we get the exact same answer we had before. So this was 1/2 we said, right? And it's 1/2 ln of 0 plus c. Isn't that really what it is? Because x was 0, the initial condition was 0, 1/2. 1/2, what happens? So what happens here? Be careful. This is e. E to the 1 equals c in this case. But what did we have for our value e, guys?
E over 2.
E over 2. So in this form here, if we solve for it like this, by including the natural log in there, we're going to have to take into account that it's a different answer here. Now, if you had done this instead, if you had taken the natural log of this side over here and plugged the initial condition afterward, let's see what we would have gotten. So we had earlier, what was it, e squared over, or e over 2 here? So that would have been right here? No? Here. So if we had put in
Get in the aisle, Karen.
e over 2 here instead.
He's way off the aisle.
Okay? If we had put e over 2 in there. If we had multiplied, guys, if we had multiplied by that 1/2, where was it? Sorry, over here. Oh, crazy. If we had put the e over 2 over here, like, who mentioned that? Christian mentioned that? And then we multiplied by 2 over here. We multiplied both sides by 2. What does that end up becoming? E. So if we had done that, absolutely, Christian, it would have worked. We still get the same answer for e there. Okay?
Wait,
Keep that in mind when you're doing this problem, guys.
Wait, the wrong answer you mean? Right.
No, again, if you had solved for c earlier, got e over 2, plugged it in there, when you move this 2 up, the 2 gets distributed, you're left with just the e at the end there. And then that e carries down. This e would have been there. And when we solve for the initial condition, what did we actually get for c? We got e, which indicates that's what that e was there. It's the same way of doing it in more than one way. Okay? Same process, but different paths to go to this. What's the second part? Domain, and what did we just talk about a minute ago?
ln can't be 0 or
Good. So my function here, my actual function is this with e. This is my actual function right here. So I say 2x cubed, yes, plus e must be greater than 0. Okay, how do I solve for x here? Just what kind of technique? I would just move stuff over, right? Move the e over.
You have a weird number. You have a weird.
Okay, divide by 2.
And the cube root.
Take the cube root. There's your domain. Okay. Now, after this, the answer key puts it as 1/2 e. I put it as e over 2. Same thing. After this, it asks for the range. What's the range? What do we say? Negative infinity, positive infinity. Okay, log functions always rank same range. Remember I told you guys last week I put that derivative table and integral table up on Facebook and that? Okay. There are other really good resources, and they're like must-knows for calculus. And one of the things they put on there is like, you must know the domain and range for all your typical functions. So for a log function, you should know that the range is always negative infinity to infinity, always. The domain is always whatever makes it positive. For square root functions, for a square root function, it always looks like this. What's my range?
0 to...
0 to infinity.
Unless there's a k at the end of it. If I had something like this,
What's the website you gave us?
what if it was like that, guys? Okay? This 2, what happened? It's you know the book series?
It wasn't me though.
Oh, okay. The link I put up to goes from. Have you guys heard of the books called like Math for Dummies, Computers for Dummies? It's a yellow book. It's in Barnes and Noble. You know what I'm talking about?
Yeah.
Yeah, they have a website. That's where the page came. So it says dummies.com at the top. Yeah, I wasn't calling you dummy. I was just referencing. So, Thanks, Rosie.
I was just telling her, I was like.
Sure. The 2 here, this 2 is my h value. So I go over 2 and I go down 4. So my function for this one would look like that. Okay, so my range would be from -4 all the way up to infinity. My domain would be from -2 all the way over to positive infinity. So based on the h and k and the vertical and horizontal shifting, your range and domain change for these kinds of functions. Okay? All right. Now,
I was so mad that it didn't work.
How well did we do?
let's look at the actual answer key real quick. I want to show you the point breakdown and how it looks.
What's the average?
Well, you know what? What was the average on the test? Christian had the highest grade. I think Christian and then Carrie and Edgar were tied for the second highest grade. The highest grade, what was your actual grade again? 70 before curve? Before curve, his grade was a 70. That was the highest grade. And then the curve just applied linearly.
28 points.
It's linearly. You want to see? Without seeing your grades, I'll show you the curve. Okay, without seeing your grades.
Exponentially.
Right? 2 big algorithms. But he just decided to get everybody.
No, I got it off already. Alright, so here's the curves from in the last few tests. So the way it works, whoops, go back. For this test, the highest grade was a 70, Christian. Okay, so I assume 70 to be around 100. I never give anybody 100 in this because nobody got a perfect score. So I gave you, I think, a 98 for your grade. Yep. So the highest grade was a 70 out of 100, so that became 100. The lowest grade before curve was a 30%. That would be around a 65, so nobody failed the actual test. Then from there, it's just scaled linearly. Then you can look at each one, they increment by about 5.7. 5.7, 5.7, I just fit a linear curve. Look at the function I wrote. I just wrote a function and what it does. It looks complicated. It references the lowest point, it references the top point, and it splits it into 7 subintervals. So imagine taking 70 minus 30, you get 40, right? And then divide that by 7. That's what I did here to get 7 subintervals. Okay? 7 or 8.
But you begin at 30 would not be failing.
Correct.
And then from there,
And then from there up to 100, it's a linear curve.
Yeah, you have.
Okay? So you can look at your grade. If you look at your percentage grade, so if you see on Edline your grade was like an 85, that means your percentage, you got about half the test right. Okay? That's what an 85 would be. If you got a 90 as your grade, you got about 60% of the test right. So if you want to see that, you can always look at that. But that's how I do it. Same for the look at the last test though. I mean, big improvement there. Last test, the highest grade was a 42 instead of a 70. The lowest grade instead of a 30 was a 9 out of 100. So that's how the scale worked for that one. Let's look at the one before that. The one before that, the highest grade was a 62. The lowest grade was a 10. So that was the scale for that one. I think the first one didn't have one. Let's see. No, the first one didn't have anything for it. First one, well, the first one was limits. It was one easier one, and God bless you. And I did the curve mentally. I didn't do it this way. All right.
Yeah, I know. I always forget limits.
So,
How many teachers do curve?
what's that?
How many teachers do curve?
I mean, the only class that really curve is this one. In physics, I'll rarely add like 2 or 3 points to your test. That's it. Okay? Only one. You know why? Honestly, the only time I curve, and for like non-AP, I'm talking about physics.
Yeah.
For something like that, the only time I curve is when I see that everybody got the same problem wrong, which means to me that I didn't do a good job teaching it, right? Everyone gets it wrong, and that's happened before, where everyone literally gets like the same thing wrong.
Well, we
So
didn't
I'll
listen
see
to
you.
you at the same time.
Say again?
Oh, we didn't listen to you all at the same time.
Yeah, or maybe there's like literally one person that gets it right, and clearly I want just one person getting a good grade.
Or one person gets it wrong and everybody copies.
That's a whole other issue, Kenny. Alright, so, what I want to talk about real quick is something we did in physics last class, and those in physics know about it. but just to generally talk, and I want to explain where we use optimization for this. So last class in physics, what we did this thing, and we could do it here in the last month if you want, and we can actually use optimization to solve it the right way, or the better way. So yours was a good idea, but there was a better way to do it. So what we did was, we took a piece of tinfoil, and I had everybody 7 by 7 piece make a boat out of it. And the boat that held the most pennies won. And the whole idea was that if you want to hold the most pennies, you want to make it a shape like a boat so that it's got a lot of buoyant force. The formula for buoyant force, which many of you know in physics, the formula for buoyant force is the density times the volume times the gravitational constant. The density of tinfoil is the same. The density of the water is the same. You can't change this. The gravity on Earth is always gravity. So the only thing you can alter is the volume. So if you maximize the volume, you maximize the buoyant force. Think about it logically. If this number is a 2, and I multiply it by 1 and 1, it's just 2. If it's a 4, it makes this go up. If this is 10, it goes up. So the goal for today's lab in physics was to find the maximum value of the volume. Edgar, what did you do?
Maximize the area.
He maximized the surface area because he thought, all right, and this is a good thought. If there's more surface area, there's more pressure like pushing back up on it, right? It's spread out more evenly. And he got a pretty good result. How many?
87.
87 pennies. And it was a piece of tinfoil this big and held 87 pennies. Now, with that said, what would be your, again, you're given a piece of tinfoil, 7 inches by 7 inches, and you are told to find the best boat to hold it. And I want to maximize volume. That's my maximize function. So what's the volume of if say you're doing a prism, he did a prism. What's the volume of a prism? Good, LWH, right? So the function you're looking at is LWH. But what are your constraints now?
7 by 7.
Okay, the material constant right away, that your surface area is going to be 7 by 7. Now, Edgar, what did you do? What did you visualize this as?
Little corners and
Good, remember the corners we did? We call that X, we call that X. We did the corners like that. We did an example in class, if you look back to your optimization notes, where those are all X's. And we cut off the corner and folded it up. Okay, that was the one where the box got folded up to maximize. So Edgar actually did this by hand and came out with the numbers. Can you? Yeah, thank you. So he did exactly that. He said, let me just look at the corners of it, take away the corners, write my volume function, solve for my constraint, plug it in so that it's all the same variable, take the derivative. He took the derivative and he got x equals negative 1.5. Now, that maximized the surface area, obviously. That would not be the same solution for volume here. Now, that's an example. There are many other examples. But what I want to talk about is now logical thought. So what did I tell you after that here? When you said that this is my answer, and I said, what should you also consider? And I'll show you what the tinfoil is. I have one piece left.
The material, the density? The under it?
Well, actually, I'm not going to use this. I'm going to see.
Is that it?
Is that it? What was it?
This density of the material? The base, like the amount of material, like...
Yes, good. So 7 by 7, just so you know, is about this big. Obviously, mine is stronger because there's more than one sheet now, if you want to do this. So everybody got one sheet of tinfoil, but it was not folded. It was one sheet like this. So Edgar started folding up the corners, got the corners folded up, made the construction out of it. Now, that is logically the most volume. But if you only have one thin layer along the bottom, that's what happened to yours. How did yours fail? The buoyant force didn't screw up.
weight in the center.
What happened?
Too much weight in the center.
They started putting the pennies in here, and theirs was a boat like this. You know, it was actually, all the corners were pulled up, it was actually a square, he folded it perfectly. Okay? And when they put the pennies in, Julian started putting them on the side, it worked, but then he put like, what, like 5 in once? And what happened to the center?
A lot more than that.
The center went whoosh, and it didn't sink though. It just started like that. Then they started, and Edgar said, reinforce the sides now, so it'll balance back out. So then they started putting pennies here, and it started to float up a little bit, come back up. And the buoyant force started to actually help. But then eventually what happened? It just went whoosh, and it sunk under. Okay? So your idea here was to maximize your volume. And a lot of people in physics, they don't realize that right away. The area helps. You know, you want the most area in the bottom, but it's the volume that really matters. All right, for a preview of what's going to happen. Tomorrow we're going to start the next topic on integration. We're going to look at applications. We have 3 things left. That's it. Area between curves, volume revolving this way, volume revolving this way. Okay? And volume is an interesting one. Volume is one where you take, like, imagine you had like an XY curve like this. Okay? And imagine if you took this curve and rotated it around the Y-axis. What shape would you get? a dome or like a bowl. Think about it this way. Imagine if you had this area filled in right here and you revolved it like that. You're going to get like a hollowed out, imagine like a cube, and you hollow out a bowl out of it. That's what it would be. Because this inner part, you're revolving like this, okay? So you get this empty inner part, God bless you, and this area all on the outside. So you get this symmetric look on every side. So you'd end up getting this bowl in the middle. That's what our next real goal is to look at bodies. It's a really easy integral. It's difficult to think about, though. So what we're going to do is we're going to actually do some hands-on stuff to see it. It makes it a lot easier to see than actually just do it on the board. Okay? Questions? Who missed it? Houston? Okay. Remember, guys, next week, Tuesday, we do have class. I know it was last week before break. We have class on Tuesday. If you are, okay, so I'm trying to